Good afternoon. My name is Midshipman First Class Lau. I'm a senior at the United States Naval Academy, and I'm commissioning into the Marine Corps as a cyber warfare officer after this.
I am also a senior at the United States Naval Academy, and I will be commissioning into the surface warfare community.
My name is John Janess. I'm also a senior at the United States Naval Academy. I'll be commissioning into explosive ordnance disposal.
Okay. With the introductions out of the way, we'll go ahead and get started on our presentation. So today we're going to be presenting to everyone our senior capstone, which we've called a quest called Tribe. So our project's goal is to leverage a transformer-based sequence-to-sequence autoencoder to group malware families into logical groups that we're calling tribes. Now, why is this important?
So an analogy is helpful to explain the importance of our project. So in the Navy, fires on ships or submarines are horrible. So in order to fight the fire, you need to triage that process. The Navy has Class A, Class B, and Class C fires. An alpha fire, like on the top left, would be paper or wood, what we're normally familiar with as fires. A Bravo fire would be a grease fire. Charlie fire would be some sort of electrical issue. And in order to fight those fires, you need to properly triage them. So for example, if you pour water on a grease fire, no good. That's going to cause it to expand more. So if we relate that to this malware issue, it's important for security operations centers to triage malware. For example, if you take a wrong step when attacking a Trojan, you can possibly cause more damage to the system. So it's very important to understand the behavior of malware. So our project seeks to better classify and group malware because currently, as you'll see on the next slide, there's a ton of malware families out in the world.
So before we get to our malware corpus, we're just going to start where all good research should with related works. So first thing we did is we wanted to see how autoencoders are being used in the classification space. What was already being done in that field? So we found this first study, which is looking at bird sounds and classifying them back to the original bird. In that study, they had great success, like getting it, clustering all the specific noises back to the specific bird. So we're like, okay, how does that apply in the malware field? And we saw malware, a lot of papers on malware being used, or autoencoders being used for malware detection. So we saw a little bit of gap in the literature, and we were like, okay, let's try to apply an autoencoder with clustering and see what results we can produce there. While we were doing it, we had like an oh crap moment. November 2024, so we started this earlier in the year. We realized that a paper came out that was very similar to what we were doing, but ended up being slightly different. But what that showed us was that there was a bunch of different processes in there that helped increase the accuracy of autoencoders in this specific problem space. So we'll talk about that a little bit more specifically later. Onto our methodology.
So the process that we took is we first collected malware samples. So those are around 400,000 Windows malware files. We made them inert. We'll talk about that in a second. Our second step was then to create the autoencoder. And then once it's fully trained, you can run a file through it and create an encoding. And you can then, with those encodings, cluster them. And a big part of clustering, as Chris will talk about later, is internal and external validation. So the internal would be making sure mathematically that these clusters make sense. The external validation is important to our project because it will make sure that the clusters make sense. So are all these malware families, is this one cluster? So like, for example, the red group, do they all have the same behavior? And that's going to be more of comparing the descriptions or the malware families themselves. That's an external validation. Fourth, if our clusterings are effective, we would then make a tool that a security operations center could use to then fight the fires like earlier, and they can take steps to quickly triage and attack malware at the source. So the malware corpus that we downloaded was from Malware Bazaar. Again, over 400,000 Windows malware files. We reduced them down to the .text section. So that's only the object code, and that helps it keep its meaning but become inert. It can't run on whatever device it's sitting on. The size breakdown's in the left, but for brevity, I'll draw your attention to the pie chart. So just in the 400,000 Windows malware files, these are all the families. So we got 10 of the most common. And if you look at the brown slice, there's almost 6,000 other families. So just in that small data set that we've grabbed, that just shows you all those could be different types of fires. And it's really helpful for Security Operations Center to know what they do to quickly address the problem.
One of the recurring themes throughout the day and throughout like the data conversation was how do you make data like how can other people access your data later? So we did put all this work and time into stripping this data set. So we plan on making it available afterwards as well. On to the technical portion of our project. So for our autoencoder, we modified a Python transformer to run as an autoencoder. We take in a 200 kilobyte file. I know it says 200 megabytes up there. It was a typo. We have a 200 kilobyte file input, and that gets compressed down to a 64 dimensional latent space encoding. And from that encoding, that's what we do the actual clustering on. That's where we do all of our data analytics. And what we're hypothesizing is that will be representative of the original file. That's what a couple of the other studies have already shown us. In order to train our autoencoder, so the basic function of an autoencoder is it'll then take that latent space output and it'll try to reconstruct the original file solely based on that 64 dimensional latent space encoding. That's what we're calling our reconstruction value. And then finally, with each file, the autoencoder trains itself using cross entropy and stochastic gradient descent, which is pretty standard with autoencoders. Now, as for our results, so we went through, we had on our first epoch, we had really good results, too good, like 100% reconstruction rate. And we're like, that's probably not right. So we realized we had a coding error, and about 7 days ago, we had to completely restart our entire training process. So at this point, we've gone through about 3,500 different files, and we're getting about a 20% reconstruction rate, which is 50% more, or 50 times random. So we're optimistic that we'll continue working, but we run into some limitations with hardware and just in time that we have to do this. So we were allocated for the project a dedicated GPU, and even with that dedicated GPU, we've had some limitations. First of all, it's time. It's taking a long time to train our model, and we just don't have those additional resources. And then you may have seen the 200 kilobytes, and we talked about it a second ago. We had to truncate every one of our malware inputs to 200 kilobytes just on a memory limitation with our hardware. About 25% of our data was just about at that range of 200 kilobytes, so about 75% had to be truncated.
So despite the faulty architecture of the initial autoencoder, we still decided to make a pipeline for the clustering. So these are the two main things we use, which was UMAP and HDB scan. Essentially what UMAP did for us, it took the 64 dimension latent space and compressed it down to 2 dimensions. And while it does this, it also retains both the local and global data, which makes it really good for unsupervised learning. Next, we applied HDB scan to the results of UMAP. And what this does, it brings out the actual clusters. A common misconception is that UMAP might seem, as in the diagram shown here, that UMAP might seem like a clustering algorithm, but it's not. It just reveals the natural clusters within the data, while HDB scan will actually reveal the clusters themselves. And at the bottom, it's just a kind of brief how we use them together, both UMAP and HDB scan, after running the malware binaries through the autoencoder.
I'm sorry, but we are out of time. So if you guys could wrap it up, that would be very good.
Good to go. So we aren't done. We have the testable hypothesis and the procedural methodology that we want to continue with. We're just waiting on our neural net to continue being training. We're excited to see if our hypothesis will test true, and can't wait for the results and see how it'll impact malware triage. Thank you.
All right.
Oh, one last slide, sorry.
Okay, so we do have 1 minute for a question if anyone has one, and then also, I'm sure a lot of folks will be sticking around afterwards, so you guys can converse and ask questions then as well.
We'll also be here for the poster session later.
Perfect. So, any questions from the audience? Okay, then I have one. What's the most interesting finding that you have so far? Finding and or sort of maybe even a challenge that you've encountered?
There you go.
Yeah. So in the data aggregation process, I would say a lot of the, even just in that 400,000 number of malware files, we found some of them don't even have families. So they were flagged by Malware Bazaar as being malicious, but around, I think it was 2,000 of the files had no family at all. So I think it'll be interesting once we train the autoencoder to see if they fit in already pre-existing or a tribe that we determine.
Okay, cool. Thank you.